I just want to indicate, typically we do a group photo. I think you would have seen in the agenda. So after Matt's talk, since this time we are doing hybrid, we have sent a note to all the people who are joining online. They will turn on their videos. So we'll take a WebEx picture first. And then all of us will walk. I'll show you, like we'll go to the front of the building. So this is where we'll be taking a group photo. They have OSC has arranged all those things. So please don't leave. We want to make sure that everybody is there. And then we'll go for lunch. Okay. And I tell that, all of you, barrier synchronization. I don't have to tell you, all of you know. So unless everybody reaches there, we can't take the photo. Okay. So, so that is a barrier sync. How fast we can achieve that. It will be done in a high performance manner. Okay? So with this, let me introduce our next speaker is Matthew Anderson from Idaho National Lab. He's part of the high performance computing group at INL with specific focus in supporting university and industry users. He gave a very short bio, okay? but Matt has been there at INL for many years, and we have been in touch with them in really trying to see that how their workloads can actually get accelerated. And let's welcome Matthew, and then he will be sharing some of his experience. Welcome.
Thanks, Professor Panda. I should have updated that. I'm the manager for high performance computing at Idaho National Laboratory, and I want to second Adam's comments that everything you do has a direct impact on a large number, especially in nuclear energy. Idaho National Laboratory we are the site for nuclear energy research, and MVAPICH is the tool we use, both for industry and university users, principally for the industry users. So you have a significant impact. You may not know anything about nuclear energy, but you do have a significant impact on nuclear energy. I did appreciate Adam's comments on the files. I had a user last week who tried to copy 25 million files. So 200,000 sounded small to me. And that's not unusual for nuclear energy users. Okay, so Idaho National Laboratory probably doesn't figure on your top 10 list of national labs, so I'll give you a quick update where we are. We operate about, we're kind of a mainstream system. We manage about 155,000 cores. Our systems are not leadership systems. They're mostly CPU-only based systems. The nuclear energy industry is generally risk averse. So that's probably a good thing. So we do have a few GPUs, but we're mostly CPU-only systems. And we operate about 3 years behind the leadership scale systems. We have about 1,200 users. About 20% of our users are industry users. So the work you do on MVAPICH directly impacts the work that Westinghouse does, or GE Hitachi, or NuScale, or TerraPower, or all the other major nuclear energy operators and researchers. We have about 20% university users, and then the rest are national laboratory users, about 1,200 users. Again, the focus of the system is nuclear energy. About 80% of the cycles that we use are for nuclear energy, and about 10% for renewable energy. Just a little bit about our systems. This is our data center on the right. On the blue over here, you see the nuclear energy. And then a little bit renewable energy, energy environment, little fossil energy. These are our systems that we operate. Again, you notice just not a lot of GPUs. We're mostly a CPU-only system. We delivered over 1 billion core hours last fiscal year. Systems have about every single core has about 5 people waiting to use it. So a lot of oversubscription. Again, most of our usage is coming. University users tend to use a little bit more. And we have a lot of industry usage, so compliance, regulatory testing, transient testing on the systems, all that's going through nuclear energy developers from around the world, from Canada, from Japan, from US. We've got all sorts of people using our systems. And why do they use our systems? Well, we provide it for free. All our cycles are provided for free to nuclear energy users, the nuclear energy industry. And the deployment of MVAPICH 2.3.5 was a watershed moment for us. It involves some important patch fixes that Hari helped us with last year and have made a very significant impact. So this is on the right is the slide I showed last year at the MUG meeting, just showing the usage of the MPI libraries. We're seeing the usage over from 1st of January 2021 to 1st of September 2021. And I went ahead and redid that plot. Didn't use the same font or scale, but gives a basic idea. Essentially, we've seen widespread adoption of MVAPICH2 2.3.5. This is the one that had some critical bug fixes for our systems that enabled us to really deploy this for our industry users, for all our fuel characterization and other codes. So rapid adoption of MVAPICH 2.3.5. So what is driving all this usage? So the Moose framework is the toolkit. We don't have a lot of software engineering going on at Idaho National Lab. This is the one software toolkit we develop. The Moose framework is it's both a finite element and a finite volume framework. It's the core of almost every single nuclear energy simulation going on. So it's really, really popular in the nuclear energy space. We don't see it really used much else. It was based on Ben Kirk's libmesh and PETSI. So those are the key toolkits. And we've worked closely with the PETSI developers to try to tune, and we will send this to our best practices, the MVAPICH best practices. I think it would probably be useful to share some of those configurations. So here's our herd apps. This is what is, for those working on MVAPICH, you might wonder, well, what are you doing with this? What is really driving all of these? The Moose framework, every single application is given an animal name. And so here you see all these animal names. Some of them are mythical animals, griffins and anyways, but most are, I guess, some inspired by Idaho, others are just dreamed up. Bison, nuclear fuel performance code. Blue Crab, that's nuclear plant systems analysis. This is for light water reactor sustainability projects. Obviously, light water reactors have been around a long time. Want to keep them running safe. Griffin, the neutron fusion solver. Direwolf, microreactor analysis. Microreactors operate in 1 to 8 megawatt scale, so these are not your big gigawatt reactors. They're smaller scales. You can even hook up an HPC data center to one. Idaho National Labs built about 50 plus different reactors, and they've got a microreactor project underway right now too. Advanced thermohydraulics, heat pipe analysis. Again, heat pipe's pretty crucial for your SMRs, small modular reactors, and microreactors. So this is where we're deploying MVAPICH2. All of these we build against MVAPICH2 and actually tune directly. So we're kind of tied to MVAPICH2 for all these applications. We'll pre-compile the application, we'll do all the prep work. Industry users tend to come in with very little HPC experience, tend to use Windows. They'll come onto our systems to do some sort of transient testing or compliance, regulatory testing, or research development on a new type of reactor. And they will use these as canned products. So they're not developing, it's not software engineering developing, they'll actually use it to get a specific answer, engineering type work. And this will frequently take months, weeks to months of simulation time. So they're very involved simulations. And small improvements in performance make big impact in the science in this particular regime. The codes, there's still development going on in the codes, but they're actually really used for engineering purposes. And a couple images down there from the output of some of these systems. So working with Hari last year, we really worked hard to be able to find the best way to compile MVAPICH2 to be able to get the best performance we could on our systems. This is actually what we use to compile it. We do use the GNU tool set for compiling all these tool sets. This is the new edition from last year. The past year, with the release of 2.3.5, we've changed a lot of the Moose framework in terms of the mesh initialization to overlap communication and computation. So we use heavily MPI, ISend. And that has caused some problems. We've had some challenges, certainly with some of these engineering codes. At larger scales, we are seeing more frequent hangs in startup in Moose framework. So we worked closely with Nick and Hari in the past year, and we decided to turn off the shared memory pathways. This, of course, has performance consequences. That is the way we've been operating. We hope to get back to turning those on. This is how we operate and tune MVAPICH for the nuclear industry user. Again, those tools you saw earlier, this list, all of them are operating in this scale, with these settings now. Okay, so what do I mean by aggressive asynchronous communication? So the MUGE framework, you might think of it like an asynchronous multitasking system built on MPI. Okay, so that means lots and lots of very small messages, way more than you would ever imagine for an MPI code. Usually MPI code, you think of, I want to send lots of big messages, or small numbers of big messages, or relatively small numbers of big messages. I don't want to send lots and lots and lots of small messages. Where does it make sense to send lots and lots and lots of small messages when you're trying to extract concurrency where there isn't much to extract? That's where it makes sense to do lots and lots of eager sends. So here's a little pseudocode. There's actually not any work in here. It's just illustrating basically the context that we can use MPI IS send a lot, probe and receive, or do work. Go ahead, Hari.
Thanks. So one note, it is never just me. It's always a group effort. Even though I send the reply, we discuss in the group. So
sure.
Kudos to everybody. So when you say small messages, what is the average message size? Like, is it like maybe like 4 kilobytes, 8 kilobytes?
Oh, smaller.
Really?
Yeah.
Teeny. Okay.
Teeny small. So when we say MUGE framework, you should think in the back of your head, this is like Charm++ or something.
Okay.
This is like built on MPI, right? This is a really small, lots and lots of small messages.
Okay. Cool.
Other question? Oh, sorry. Go ahead. Were you done?
No, go ahead.
Okay. This one here? Oh, this one. Yeah.
So most of the applications here use PETSI. Is that true?
We do use PETSI underneath. Yeah, that's right.
Okay. So what particular solvers do you use? Do you know?
We use several types of solvers there, but it's mostly GMRS.
But do you use a preconditional?
Yes. Yeah, absolutely. And we'll take preconditioners from Hyper too. Yeah. There was another question? Nope. Okay.
So have you guys done any, let's say, profiling of the entire, so we know that the MUGE framework uses like ISN and IS receive, receive and iProbe, but internally, since you guys are using PETSI will probably also use MPI. So do you have an idea of the kind of communication PETSI does? Is it like?
To some extent. Now, wouldn't it be great if I could hook up Tau? I guess Samir is going to give a talk later on this and be able to get a clear profile of what's Moose and what's PETSI.
That's exactly what I was hoping.
And what's libmesh, right? Because it's a messy thing, right? I mean, the libmesh isn't even developed anymore except at INL, right? And so you've got all these different pieces and who's taking care of what, and then you've got a lot of asynchronous communication. So peeling back the layers of the onion inside of Tau, I don't think it's possible right now. I'd love to do that. But.
Sure. Thanks.
All right. So so Moose applications, we are tending to see the virtual buffer running out of memory. So when you do an eager send, what happens? Well, it copies the small message to some buffer and then says, I'm done.
Okay.
When in fact the communication hasn't happened yet, right? And you do lots and lots of very small messages, you're going to fill up that buffer. And then it's going to hang. And so what could you do? Our initial plan was, all right, well, let's just try adjusting, the IBA eager threshold. Just make it really, really small. Hey, set it to 0. Then there's no such thing as eager messages, right? And sure, you can fix it that way.
But performance is horrendous.
Yeah, but it hurts your performance. So anyways, we've been working, the best solution so far has been turning off the shared memory pathways. And this is what all our users are doing right now. We actually turn off the shared memory pathways to enable these simulations to move forward. What's the state of the art right now? Well, there's obviously a lot of work in the nuclear energy industry moving towards SMRs. There'll be an SMR built in Wyoming, a small modular reactor. There will be microreactors built in 2029. There's one being built right now at Idaho National Laboratory. Huge amounts of transient testing going on. So that's why we have so much usage on the system. Go ahead, question.
Sorry about that. So you said you don't use shared memory. Do you use a larger count on the PPN?
I just have to say it one more time. I didn't quite hear it.
Can you use the mic, please?
Okay. Do you use a large number of PPNs on the application you run?
Typically about 48 core. Yeah, 48.
48 cores
Yeah.
per
Yeah.
And in that case, you still don't think shared memory helps?
Well, it would help, but this is absolutely.
But with this flag, you basically
Yes,
turn
no,
off
we see performance, there are performance consequences, negative performance consequences to turning off the shared memory pathways. Yeah, definitely there. At this point, performance is pretty good. We lose some by turning this off. Okay, that we're going to lose some performance. This is in part, we got very aggressive and with the eager messages, right? Things are working really well. Of course, we don't have a GPU route, right? The nuclear energy industry generally is not going to pay for huge amounts of software engineering to convert all these codes to some sort of heterogeneous operation, especially when they're very risk averse. They want to be, verification and validation is very expensive in the nuclear energy industry. And so there's, you don't want to jump on the latest accelerator technology when the software engineering costs so much. So yeah, we do lose a little bit of performance because of that. We'd love to find a solution. Go ahead.
I was wondering, how did you figure out, it was the small messages that was causing the problem? What profiler did you use?
Let me show you. This guy right here, right? I can always adjust that. I can turn off eager messages that way, right? I can set the size to be 0, and then every single message, there's no eager messages anymore. That's the threshold between, deciding. So that's how you can kind of, empirically figure it out by adjusting that.
Thank you.
Okay, so we appreciate the continued support from Hari and Nick and the whole team on this. So the MUGE framework, which is the tool for nuclear energy now, it is the tool for advanced reactors, testing compliance, and everything else in between. Nuclear fuel, also fuel development. So all fuel testing, new fuels, everything is directly built on MVAPICH2. Everything. So everything you do is directly impacting the nuclear energy industry, so that you know. And it does involve, of course, LibMesh and PETSI. The version of choice now at INL is 2.3.5 because of the bug fixes from Hari and team last year. We really appreciate that. We are hitting issues. Moose is behaving like an asynchronous multitasking framework, and that is causing trouble with the VBUF. We're running out of VBUF, and that's causing us some performance issues.
So we are working on a solution for that, so that you don't, let's say, run out of memory. Hopefully, we should have that out, and we will definitely get back to looking at what that issue with the shared memory support is. We are glad that it is running without shared memory, but we definitely want it to run with shared memory so that you don't face issues, and we will definitely get back on that. Thank you. And
Go ahead.
You mentioned small messages. Could you tell how small they are and where in your application the need for such large transfer of small messages arise?
It has to do with the partitioning of the mesh, and that's where a lot of the small messages are coming from, and they're under 2 kilobytes.
What?
Under 2K. Yeah. Go ahead.
So Matt, can you please show the pseudocode one more time?
One slide up? Yes.
So maybe this is not the full code. So my understanding is the left-hand side is the sender pseudocode, right? And
Yep.
the right-hand side is the receiver.
Yep.
For the left-hand side, is there a corresponding weight?
Is there a corresponding weight? There is work that would be happening on the iSend side, you would be overlapping work with communication. There's not there's the check and receive here. So you're calling this check and receive routine, which is on the right-hand side. And that's where you're going to be calling, you're checking, you're running the probe. If the message comes in, you receive it. If not, go on.
So we are sending a synchronous send message.
You are sending, asynchronous messages, IS send, And then you're testing, it's almost like running a thread constantly in the background, listening. Hey, is there a message there? Is there a message there? Is there a message there? Of course, you're not doing that entirely because then you're putting some work in that thread as well.
Okay, but should we not be calling a wait function for that I send?
Well, you have the receive on this side here, which is not an I receive, right?
I'll talk to you offline.
Okay, sure. Any other questions? Again, you guys are doing fantastic work. Really appreciate it at Idaho National Laboratory. You may not realize the impact you have, but it is a very significant impact. Thanks so much.
Thanks for the wonderful talk, man.
We'll now go to